Now today we're going to continue talking about probability distributions, and this time we are going to talk about the binomial probability distribution. Binomial probability is similar to geometric probability. As you can see here, and I clipped this from the book, so you can find this in the book as well. We are talking about Bernoulli trials. That means a few things. We need to have two possibilities only: success and failure. Those probabilities need to be known. They need to be fixed. That means they need to not change based on going from one trial to the next. That means the trials need to be independent of each other. The result of one trial is not changing the probability of the next trial, and that would make them Bernoulli trials. And so you can see we have some variables defined, things we talked about last lesson or in the past. So here we've introduced n, the number of trials. P again is the probability of success. Q is the probability of failure. Again, on the formula sheet, Q is referred to as 1 minus P. So you need to be able to identify the probability of failure in both ways, 1 minus P or Q. Honestly, for me, I don't care which one you use, but I'm going to use Q for our purposes, and you can see that Q is going to be used in some of these calculations. And again, this capital X is the number of successes. And so in the last lesson in geometric probability, we were looking for the probability of a first success. When we look at a binomial probability, we are looking for a total number of successes. So we are interested in, let's say, what's the probability we get 3 successes in this number of trials? What's the probability we get 5 successes in this number of trials? So it is about the number of successes rather than the first success. And that's what makes the difference here. Just like in geometric probability, we were able to calculate a mean or an expected value. This time we multiply the number of trials times the probability of success. We can find a standard deviation. We take, and I hope you can read that. If you can't, I apologize. Standard deviation is the square root of our number of trials times the probability of success times the probability of failure. Again, on the formula sheet, you might see it this way. It looks different, but it's the same. Just a different way to represent the probability of failure. So again, we are going to use our calculator as a tool to solve these. It's a good idea right now for you to take a minute, read this problem, and then we'll talk about how we can solve it using the binomial distribution. So we're back to our spam email problem. And the first thing we want to know, or what we're told is this time we have 25 messages. We still have probability of success of 0.91. Or I'm sorry, that's a probability of failure. Remember, our probability of success for getting a real message was 0.09, so Q is 0.91. This time N is 25. We didn't have an N last time because we were just looking for a first real message. This time we're going to be talking about how many real messages out of 25. And so when we look for our expected value, we're going to take our number of trials and multiply that by the probability of success. So in this case, we have 25 trials, and the probability each email is a real one is 0.09. So 2.25. We should use our units. So when we open our inbox and there's 25 messages, we can expect on average to get 2.25 messages that are legit emails we need to spend time on. To find our standard deviation, we are going to multiply our three values together, 25 messages times the probability of success times the probability of failure. And so you might realize that we can actually take this previous answer and multiply that by the probability of failure, and then we can square root that to find our standard deviation, 1.43. So we have an expected number of messages, that's 2.25 out of 25, with a standard deviation of 1.43 messages. And so the last part of this question was, we want to know the probability out of those 25 messages that we'll find one or two real messages. And so we want to know the probability that our random variable x is equal to 1 or 2. And so what we can do here is we can find the probability of each of them and we can add them together. We will talk more about this, but OR means to add as long as our trials are independent, which they are. So we're going to take the probability of x being 1 and add to that the probability of x being 2. So this is where we're going to use our calculator. We're going to hit second vars and get to our distribution list. I like to arrow up. Let's get to the bottom, and you can see geometric there is at the bottom. We're going to arrow up a little bit till we get to binomial. So you can travel there however you want. We're going to use binomial PDF. We've got 25 trials, 25 emails, probability of success of 0.09. And we're going to do this twice. Once for one email message, we want to know the probability that we see only 1 out of 25, and then we'll do it for 2 email messages. And there we get 0.233978849. We'll round that later. Let's go and do this again. Second vars, binomial PDF. Let's change our x value now to 2 email messages. And so before I do any rounding, I am going to just add those 2 probabilities together. And so I get a final probability of 0.5117. We'll do 4 decimal places. So that means we have approximately a 51% chance of reading 1 or 2 real email messages if there are 25 of them in our inbox. So take a minute and read this one. We're back to our type O blood donors. Take a second and read this. So again, we had probability of success here. P is 0.06. We had 6% of people are type, I think it was type O, or the universal donors. Q is 0.94. And so we have 20 donors that showed up, so N is 20. And so we are talking now about a total number of type or universal donors out of 20. And so if we want to find the mean, we would multiply N times P, so 20 times 0.06. And get 1.2. So on average, out of 20 donors, we can expect to see 1.2 donors. And then for our standard deviation, we're going to multiply or take the square root of NPQ. So the square root of 20 times 0.06 times 0.94. And we will get a standard deviation of around 1.06 donors. So that's our mean and standard deviation. And so now we want to find the probability of having 2 or 3 out of 20. So again, we can find the probability of each of those, and we can add them together. And so we can go ahead and do our second bars, find our binomial PDF. We have 20 donors with a probability of success of 0.06. And we're going to do this for 2 and 3. So go ahead and do this on your own. I'm going to pause and do this. You can pause and do this on your own and then come back and we'll check our answers. So if you did this correctly, you should get, for 2 donors, there's your probability. For 3 donors, there's your probability. And then we're just going to add those two together to get a final probability of 0.3106. And so that is our probability that if we have 20 donors show up to donate blood, that there's a 0.3106 probability or a 31.06% chance that 2 or 3 of those 20 people will be universal donors. So please, if you have any questions about this, please ask. Stick around for the problems at the end. Make sure you work through those, take your time on those, ask for help if you get stuck. I'm glad to help. As always, take your time on these, and good luck.